Now that we've looked at muscles at a microscopic and a macroscopic level, we can start to look at how muscles work at a more functional or biomechanical level. Before we start, I just want to draw your attention to this top right-hand image here of that hopefully you remember is referred to as a sarcomere. And sarcomeres are the fundamental functioning unit of a muscle. They're a tiny little microscopic unit, but the actin and the myosin filaments within the muscle work together to ultimately make a muscle shorten. And that's the take-home message that I want you to carry through this video, is that muscles, when they produce a force, can only shorten. Biomechanically, what that means is that if a muscle is going to produce a force, it can only then pull. It can only pull on bones. It can't push. It can't push bones apart. It can only pull on bones and draw them closer together. And that is formed by myosin. Here, the myosin is a purple filament here, pulling on actin, and you can see here the difference between these two images is the gap here between the top image has been closed as the sarcomere has shortened. That's what happens when a sarcomere uses energy and actively contracts a muscle. So just remember, only pull, can't push. A muscle can only produce a force to make it shorten. So let's have a look at this functional example here in the middle. And hopefully you can appreciate that on the left-hand side of these images, we have a picture depicting the bicep muscle. So this one here and this one here. And on the other side, we have the tricep. The tricep, which is this one here and this one here. And the bicep is referred to as an elbow flexor, whereas the tricep is referred to as an elbow extensor. Because the prime function of the two muscles, the bicep, is to draw the forearm up closer to the upper arm and rotate the forearm in a clockwise direction, whereas for the tricep, the prime function is to draw the forearm away from the upper arm and rotate the elbow in an anti-clockwise direction. So they're referred to as antagonist muscles, antagonists, because they oppose one another. If one contracts, the other one can resist that motion. And that's called a phenomenon called co-contraction, which is a really important aspect of the way muscles work that we'll cover in another video. So let's have a look then at how these biceps and triceps actually function, as the video name suggests, as levers. So remember our rule for sarcomeres, that the muscle can only shorten. And if we assume here that the attachments at the top of each image of these muscles are fixed, so those bones aren't going to move when the muscle contracts. The attachments that are going to move are these ones down the bottom here. Okay, so the attachments that connect to the forearm bones, the radius, and the ulna. So when these muscles contract, they can only shorten, and therefore the force that they're going to produce is in an upward direction. Up. Because remember, they can only shorten, so they can only draw their ends closer together, they can only pull, and so even though they're on different sides of the elbow, they are both pulling in a vertical upwards direction. So that's the force. They are the forces that the muscle is producing. So how does that translate into elbow flexion in the case of the bicep, or elbow extension in the case of the tricep? Well, now we need to look at our joints again. And in biomechanics, what we really start the analysis with for a biomechanical analysis is considering a joint center. A joint center. And for the elbow, it sits at the very end of the upper arm bone, the humerus. And it's basically where the central point that the forearm rotates around when it moves. So the joint center is really important because it dictates what lever arm, the muscle has. So if we look at the lever arm of the biceps, you can see we've got this distance here between the joint center to the force. So that is the biceps lever arm. The triceps lever arm is this smaller one here. And on the other image, we've got the biceps lever arm here and the the triceps lever arm here. So in order to produce a rotation, a movement, either elbow flexion or elbow extension, first of all, we need a muscle force. So we've got our muscle forces overlaid on the muscle here, and then we have the lever arm. And with these two things combined, then that causes rotation of the joint. So hopefully you can see in the case of the biceps, we've got the lever arm pointing out to the left-hand side, and then the biceps force pulling up in this direction. And so those two things combined cause the forearm to rotate in this clockwise direction. Whereas for the triceps, the lever arm here is coming out to the right, the force is still up, and that is why the triceps can act in an anti-clockwise direction. So the way that a muscle produces movement is through a pulling force that acts as a lever around the joint. That's why the structure of the joint is so important, because it dictates the degrees of freedom that the muscles can produce movement through. And then the muscles are able then to produce that movement with the combination of a muscle force and a muscle lever arm. Now, all muscles in the body act in this way. They all produce a straight pulling force that is coupled with a lever arm that produces a joint rotation. And so a good exercise is to have a look at an anatomy text, or to even consider the muscles in your leg or wherever you would like to visualize these muscles, and consider how are these muscles acting as levers, where they are producing a straight pulling force but producing a turning or a rotary movement around the joint.